to deal with such a big number, we have to rely on an automatic classification. And so here I focus on XMM Newton, but this can be applied also to other kinds of catalogs. And the expected content of your X-ray source catalog, given it also includes extended sources, for example, is about a majority of AGN and stars, generally speaking, but also X-ray binaries, cataclysmic variable, galaxy cluster, and so on and so forth. So let's start to prepare our data. So all that you will see now is implemented in the automatic code Claxboy. So even the data preparation step that you can find on GitHub, I will show you later. Okay, so the first step of data preparation is maybe to identify a training sample while we are doing supervised classification. So we identify known AGN, stars, X-ray binaries, cataclysmic variable, depending on the choice of your classes. So that was an initial choice of classes we did for XMMDR10. And here we used, I would say, simplistic cross-match of one hexagon between the two is not so big, so it gives in principle reliable results to identify a training sample of known sources. So the second step is to identify the counterparts, so the multi-wavelength counterparts, so that we can compute, for example, the ratio between the optical flux and the X-ray flux, or X-ray to infrared flux ratio. And this is extremely important to distinguish different source types. So this is done using the NY software. This is not precise here. That was presented yesterday. Well, we can discuss it a little bit more later if you want. But the bottom line is that we use a set of optical and infrared catalog, which are listed later, to have a rather complete census of optical and infrared counterparts. Then, to add more value to the catalog, then for example, to compute physical quantities such as the X-ray luminosity, you need to know the distance of the counterpart. And so for galactic sources, this can be the Gaia inferred distances. And for extragalactic sources in nearby galaxies, you can cross-match it with a catalog of galaxies. So in our case, we chose GLADE. And so GLADE is an all-sky galaxy catalog designed at searching the counterparts for the electromagnetic counterparts of gravitational wave events. So it is rather complete, up to maybe 500 megaparsecs. And so at the end of the day, you have an enhanced catalog, a value-added catalog, with also information about the optical, about the known sources, about the optical and infrared counterparts, and about the distance of the source. So this is a list of features that we can use then by the classifier galactic latitude and longitude, the separation to the galaxy when it matches a nearby galaxy, the X-ray luminosity, the flux ratios, also some variability quantities, like, well, very basic, so maximum to minimum flux ratio computed. So they are multi-mission. They are computed based on catalogs of Chandra, Swift, XRT, and XMM Newton detections. And also some spectral, I would say, spectral properties. So about the hardness ratios and maybe also the power law index fitted to the X-ray spectrum when it is available, of course. So, so here comes the technical part. So when you have this training sample, you can plot the densities of each property for each class. So for example, this is for the X-ray to optical flux ratio, and you see that AGN and catalytic variable are nicely distributed around 0, and are well separated from star, for example. And these how to say that, these probability densities, these densities can be used as probability densities of each class later by the classifier. So now let's talk about the classification model in itself. So well, earlier than 2022, we didn't have a lot of studies in X-ray astronomy doing classification of large samples. So the largest sample were maybe thousands or tens of thousands of sources instead of the million sources detected. And so they were sometimes targeted at specific population study in a specific nearby galaxy, like M31, and also the model of the classification. So well, you know, there are different machine learning models for classification. One of the most used is random forest. This is not the one I will present now. And I would say that random forest maybe has less interpretability power than the naive-based classification. So ClaxBoy is based on naive-based classification, and this is what I will present now. So initially, if you want to distinguish, for example, between just two classes, AGN and stars, and you have this kind of distribution of the training sample for the flux, for the X-ray to infrared flux ratio, you can say, okay, all sources below -1 are stars and all sources above are AGN, but the distributions are overlapping, so this is not very a good approximation. So rather, you can compute the likelihood of the star and the AGN class given each value of the property. So, for example, if your source is 100 times brighter in the optical than in the X-ray, then the probability for it to be a star is 93% and 7% for the AGN class. This is just for two classes. And then, so you can combine the idea of the naive-based classifier is to combine this likelihood using the base formula for all properties of your catalog to obtain the final probability of the source to be belonging to each class. So when you have combined the different features, you have a naive-based classification. And so here we added a step so-called optimization, because you can also weigh more the probabilities that are the properties that are most discriminant by optimizing the quantity here. So which is basically a weight for the different categories of properties. So this is useful, for example, if you want to obtain the best results of on one specific class you are interested in. Okay, so here are some results. So confusion matrix of the classification once applied on 4XMM DR10. So you see that the classification have a really high recall and precision for AGN and star classes, but it also performs well on X-ray binaries, and it's not quite the case for catalytic variable. And so this one is for XMM DR10. This one is for Swift XRT, and this is the comparison with the random forest method. So we obtained similar performance than as the random forest, but we have better interpretability. As I will now show. So a first way to gain more meaning on the classification is to know if your source is an outlier or a typical source of your input classes. So this is this can be quantified using the outlier measure, which quantifies basically the scarcity of the training sample at this point of the parameter space. And you can see, for example, here, the distribution of outlier measures for different type of AGN. So you see that, well, because the training sample was mostly quasars, the outlier measure of quasars is quite low, but you have also liners in this training sample, and the outlier measure for them is quite high. So when you have an unclassified sources with a high outlier measure, it can be a special type of AGN if it's classified as AGN, special type of star is if it's classified as star, and so on. But also, well, more often than not, for example, spurious sources or spurious identifications have also high outlier measures. So this can be also a way to mitigate to understand the contamination of your sample. So this one is my favorite. So you can also use the marginal probabilities to interpret the classification of one particular source. So you see, for example, this source in X-ray and in optical, and it is classified as AGN with 88% probability. And you see here the probability here. So it's 88%. So it's the final probability, but you have also the marginal probabilities for location features, for spectrum features, for multi-wavelengths features, and for variability features. So so basically, this graph tells you that if you consider only location and spectrum, the source would be classified as a galactic X-ray binary. So this is a very efficient way to explain your classification as AGN in that case. Also, well, we also provide alternative classifications. So basically, if you just ignore features of one of these four categories and you have a different classification, then it is present in the alternative classification column. So you see, for example, that this source, well, it's not very well visible, but you have an extended source in X-ray, in XMM Newton, corresponding to 3 sources in Chandra, and to a crowded field in this DC legacy survey. And so the classification returns, so the classification result is extended source. But the classification also tells you that if we did not consider the location features, where did I put that? If we didn't consider the location features, it would be classified as galactic X-ray binary. So this is another way to interpret the classification. But let's now finish with some applications of the classification. So this Claxboy was applied to the whole XMM Newton DR12 catalog using an updated set of classes, especially to improve the performance on X-ray binary classification. And so you have 7 classes. So you have 2 classes for AGN, depending on the presence of information. Basically, if the source overlaps a Glade galaxy. You have stars, you have galactic X-ray binary, but also extragalactic X-ray binary. You have cataclysmic variable, and you have extended source. And you see here that the recall are very high for almost all classes except the galactic X-ray binaries and cataclysmic variable, and the precision is high in all cases. So this is very well encouraging. Well, I would say beware of spurious sources and crowded regions, because you must still use your brain to understand what you're doing. And faint sources in particular may not be very well classified when they have a lot of missing information. But if I trust the result of the classification, this is the content of for XMM DR12 with more than 400,000 AGN and almost so you see them here, and here is the the galactic latitude and longitude of the different classes. So the classification, when you're doing, for example, a population study, you may have very specific needs. For example, if you study only sources matching a nearby galaxies, you can specialize the classification on this science case. So this is what we did using ClaxBoy, but with different classes and only for X-ray sources matching a galaxy. And this was done to properly identify ULXs. So I will not give more detail here, except that the probability returned by the classification can be used to so basically what I showed earlier here is if you consider that the class giving maximum probability is the output class. But this is not always the case. So this is well, anyway, in a given galaxy, in a given nearby galaxy, sources further apart than from the galaxy center have a high chance of being background sources, and this can be computed using the log and log s. This can be quantified using the log and log s relation. So frequency of background AGN can be compared with the probability of the source to be an X-ray binary, and this we found that this is a reliable way to identify ULX and so ULX populations. And so with that, you can do actually a population study. So we published a paper recently about ULX and HLX in XMM, Newton, Chandra, and Swift catalogs. So I will just finish my talk saying that ClaxBoy is public and it's documented now. I updated the GitHub yesterday, so you can access it on my GitHub, and feel free to use it and reach me in case if you have any question. And yes, so no, sorry, this is this is not finished. 30 seconds. So this is just a teaser for tomorrow, because right now we have a value-added catalog, a probability classification, which can be applied on all sample size, and it is both reliable and interpretable. But some classes lack a big training sample. And this is why I say that machine learning and citizen science are complementary, because citizen science can be used to enlarge your training sample, but also find anomalies in your catalog. So this is done by the Klaxon citizen science platform that I will present tomorrow. And yeah, here is my conclusion. Thank you.
Okay, thank you very much, Hugo. It was amazing work. So if you have any questions, please.
Thank you, Hugo. The first question I had, I was not sure exactly what you used for test samples when you present recall and precision. Yeah. Was it really independent of your original classification? In the first case, it looked like not.
Exactly. So you're absolutely right. In machine learning, for most methods, you have to use a different sample for estimating the recall and precision, and for training the model and for estimating the classifier performance. But in this very specific case of naive-Bayes classification, you do not have such an overfitting problem, except when your training sample and your test sample are really except when your training sample and your and the sample on which you apply the classification in the end are very different. But in naive-Bayes classification, we do not have overfitting problem, because the densities of each source are basically smooth. see here we use a kernel density estimation to smooth the density for the training sample. So if we used a set of the training sample for training, we would have very similar densities and very similar results on the other part of the training sample that you use for testing. I hope that's clear, but I think we can still discuss it more if you want later.
Okay, but sorry, I didn't say who I am for the outsiders. I'm Jean Ballet. So I have a more serious question. In Fermi, it's a big industry, all this. And when my machine learning colleagues present this, I always ask them how they account for the fact that typically the sources that are used as the training sample are brighter and better known than the unknown. And they say, well, the uncertainties are entered in the machine learning thing and they account for it. But here, I don't see how you account for this.
This is not taken into account. This is why I say that these results here should not be always trusted for feign sources, because training sample sources are typically brighter. And so, for example, you can imagine that all sources the distance AGN, which is not identified, they will not necessarily have an optical or infrared counterpart. And then the classification results can be biased. The trick here, the way to mitigate this effect is to combine the different properties of so variability, multi-wavelength counterpart, spectrum, and so on. So combining these features gives you a more reliable result than if you just considered the multi-wavelength counterpart, for example. But yeah, there is always a bias when you try to classify feign sources in your test sample. Absolutely.
Okay, so we have a question at the end. Last.
Thank you. Great talk. My name is Rafael Brusco. What kind of source changes classification when you take out the coordinates? Well, the location-based features. I'm particularly interested in the choice of keeping them in, because they can introduce biases.
You're particularly interested in what? Sorry.
You use as features galactic coordinates, right?
Yes.
When you take them out,
yes.
What are the classes of sources that change classifications? Have you looked at that?
I did look at some of them. So, for example, well, yeah, well, there are several things here, because the location features include not only the galactic coordinates, but also the proper motions of the source. So do you want to remove them? I don't know. And but yeah, it would be very interesting to look more in depth into this. And yeah, anyway, we do provide here alternative classification. So you can ignore all location sources and see if that changes the classification. So this is already public in the output catalog.
Okay, so let's thank Hugo again.